This video gives an overview of Dijkstra's algorithm and does a few examples of Dijkstra's algorithm running on small graphs. So we know that Dijkstra's algorithm finds the minimum weight paths from a starting vertex S to each other vertex in the graph. Here's an outline of the algorithm. We set the cost of the starting vertex S to be 0, and for every other vertex V in the graph, we set the cost of V to be infinity. And we mark all of the vertices as unprocessed. So the cost of a vertex is the cost of the so far known minimum weight path to get from the starting vertex S to whatever other vertex is in the brackets. So the cost from S to itself is 0. We don't have to go over any edges. And at this point in the algorithm, in the beginning, the cost for every other vertex is infinity because we have not reached the other vertices yet from S. And so since as yet they are not reached, they are unreachable. The cost to get there is infinity. So we're going to call X the next vertex to be processed. In the beginning, the first vertex that we process is S. So initially we are processing S. To process any vertex X, we consider all unprocessed neighbors of X. Neighbors just means that they're connected by an edge. So the neighbors of X are all the vertices, U, etc., that are connected to X by an edge. So we consider all of its neighbors that have not already been processed. And for each of these neighbors, we define the cost of U, the cost of that neighbor U, to be the minimum of two things. The previous cost of U, whatever it previously was, or the cost of X, the total weight of the path so far up to X, plus the weight of the edge XU, whatever that is. So maybe that's 3 or whatever. So this is the weight of the edge XU, and this is the cost of the path from S to X. So this is the weight of path from S to X. So for each unprocessed neighbor U of X, the current cost, that is the current minimum weight path that we know of so far from S to U, is the minimum of those two values. Okay, so after we've updated the cost of each of the unprocessed neighbors of X, then X is processed. And when we say that X is processed, that means that we don't need to consider it again, and whatever the cost of X was, that is the cost of the minimum weight path from S to X. So X is processed, it does not need to be considered again. And now we are going to consider a new X. So the new X that we will then process is the unprocessed vertex with the smallest value of cost of X. So whatever vertex has the minimum cost among all unprocessed vertices, that is our new X. And if such an X exists, we go back to 2 and we do that again. So we do that process over again with this new vertex X. If no such vertex exists, then we are done with our algorithm. So let's see this working on a very small graph. So we've got this graph on 5 vertices on the left, and we want to find all shortest paths from S to every other vertex. So here's our starting vertex. We want to find the shortest paths to each other vertex. And we want to, at the end, highlight the spanning tree of shortest paths on this graph. So our first step is to say, okay, from S to these other vertices, at this point, the distance or the minimum weight path from S to itself is 0. At this point, the minimum weight path from S to all the other vertices is infinity because we have not reached them yet. Now we are taking the minimum of all those values. So this is cost of S, and this is cost of B, and so on. And we're going to take the minimum of all of these values and bring it down and say, okay, now cost of S is 0. And now we are going to process the vertex S. So we're now going to process the vertex S. We're going to look at each of its neighbors. So each of S's neighbors that have not yet been processed, it has 2, B and D. And so now we can update the values for B and D, that this is, at this point, the cost of B at this point is the cost of S plus the weight of the edge from S to B. And so what is that? That's 0 plus 6, 0 plus 6, 6. And similarly, the weight of the cost of D at this point will be 1. The cost of C is still infinity, so the cost of C has not changed and the cost of E has not changed. So now S is processed, so S is done. And now we're going to bring down the vertex that has the minimum cost out of all of the unprocessed vertices thus far. That's D. So the next vertex we're going to process is D. So let's process D. We are going to look at each of its unprocessed neighbors. So let's see, D has the neighbor E, and it has the neighbor B, and only S has been processed so far, so we're going to look at both B and E. When we look at B, we can say, okay, we are going to take the minimum of the original cost of B, so the original cost of B that we previously had, and the cost of the path that we took up to B so far. So that's D, that's the vertex we're processing so far, plus the weight of the edge, dB. So we are looking at the minimum of those two values. In other words, the new minimum, the new cost of the vertex B is the minimum of those two values, and those two values were the previous cost of B, which is 6, and this new cost of D is 1 plus the weight from D to B is 2, and so yes, we see that the minimum of 6 and 3 is 3, so that cost for B will be updated to 3. So we're updating that cost. What about other neighbors? C is not a neighbor, so its cost is not being updated. And E is a neighbor, so its cost will be updated. So it's the minimum of infinity, and whatever the new cost is, the new cost will be better than infinity. So the new cost is the cost of up to D so far, that was just 1, plus the weight of the edge from D to B, which is, from D to E, which is 1. So this new cost is 2. So now D has been processed, and now we are going to look at the minimum of all costs of the vertices that have been thus far not processed yet, and 2 is the minimum out of those, 3, infinity, and 2. 2 is the minimum, so we're going to be bringing 2 down, and we're going to be processing that vertex E next. We should also be keeping track of the paths, the minimum weight paths that we've gotten so far. So the minimum weight path from S to D was this. Our minimum weight path from S to E, that's the last one that we have, went from S to D to E. So that's what we've got so far as our highlighted minimum paths. So now let's process the vertex E. We're looking at all the thus unprocessed neighbors of E. So B and D are the two neighbors we'll be looking at. And we're defining the cost of, say, B to be the minimum of the previous cost of B. The previous cost of B, as far as we knew, was 3 so far. Or the other value to look at is the cost so far up to the vertex we're processing, E, plus the weight of the edge from E to B. So what is that? That's the minimum of 3, the current cost of B, and the cost up to E so far, that was 2, plus the weight of the edge from E to B. So the weight of the edge from E to B is weight 2 as well. And the minimum of 3 and 4 is 3. So that means we're not updating this value, we're leaving it as it is. How about C? Well, the previous cost was infinity, so probably we're going to be improving that. So the new cost for C is going to be the minimum of infinity and the cost so far to get to E, which was 2, plus the cost of the edge from E to C, which is 5. So the minimum of infinity and 7, which is 7. So 3 was not updated, it stayed the same, and this is 7. So now we have costs for each of the unprocessed neighbors of E. So at this point, E has been processed, and we are going to bring down the vertex with smallest value for cost, and that vertex is the vertex B, so B will be processed next. We see that the parent of B was D. This was the last place that the value for the cost changed. So here is the minimum weight path from S to D, from S to B, S, D, B. And so that is our minimum weight path. Okay, we'll now process the vertex B. So again, we're looking at all of its unprocessed neighbors. It only has one unprocessed neighbor, and that's C. So when we look at the cost for C, that is now, again, the minimum of its current cost, which is 7, and the cost up to B, which we're processing, which is 3, plus the weight of the edge from B to C, that's 5. So it's the minimum of 7 and 8, which is 7. So this is still 7. It did not change. And so its parent vertex is still E. So the minimum weight path from S to C goes from E to C most recently, so that's the parent. And now we have this minimum weight path, whatever the path was up to E, as well as the edge from E to C. And so now we would look for the minimum among all unprocessed vertices. Well, there's only one to consider, so that's 7. So we're bringing 7 down, and technically we're now processing the vertex C. We're looking at all of its unprocessed neighbors. It has none, so we go ahead and look at all of its unprocessed neighbors, and there's nothing to do. And now at this point, there are no more nodes to process. C has now been processed, D had been processed, and we are done. So if we look at the edges of this graph that are highlighted, we see that this is now a rooted tree where S is the root, and we see for any vertex X, we can look back and see what the shortest path is from S to that vertex. So the shortest path from S to B, the shortest path from S to E, and so on. Okay, let's take a look at a slightly larger example. So we've got this graph on the left. Again, we want to show each pass of the algorithm with a table, and we're going to highlight the spanning tree of shortest paths on that graph. So what you could give that a try, and we'll talk about it in just a moment. Okay, we first start by labeling the cost for S as 0 and the cost of every other vertex as infinity. Okay, now we look for the minimum cost of each of those vertices. S is 0, clearly has the minimum cost, so we're bringing that down, and now we are processing the vertex S. So we're going to look at each of the neighbors of S. So B, D, and C are the neighbors of S, and the total cost of the path from S to each of these is just going to be the weights of those edges, 8, and then 5, and 2. And the others, there's no path of length 1 from S to any of the other vertices, so their costs are still infinity. We now have processed the vertex S, and we are going to bring down the vertex with minimum weight, with the minimum weight path thus far, and we're going to process the vertex C next. So because we're processing the vertex C, that means that we do know the minimum weight path from S to C, and we can highlight it on the graph. Okay, so let's process that vertex C. We are now going to look at the cost of each of its neighbors. So we're going to look at the cost of D or each of its unprocessed neighbors, D and E. We're not looking back at S because it's already been processed. And so we now want to find find the cost of D. The cost of D is defined to be the minimum of the old cost of D. In this case, that's 5, the old cost of D, and the cost of C, which is 2, plus the cost of the edge from C to D, which is also 2, and so it's the minimum of 5 and 4. 4 is the minimum, so we are updating that value because it is smaller. How about the cost of E at this point? The cost of E at this point is the minimum of the previous value for E, that's infinity, and the new value, that's the cost so far, up to C plus the edge, the weight of the edge from C to E, which is 5. So the minimum of these two values is 7. And none of the other vertices are neighbors of C, so their values stay the same. And now C has been processed. So C has now been processed, and so we can bring down a new vertex of smallest cost that has been thus far unprocessed, and that would be D. So we are going to process the vertex D next. Since we're processing D, we also know that we have now the minimum weight path from S to D. We add the edge where D was most recently updated, which is the edge CD. And so we're adding that edge, and now this purple path is the minimum weight path from S to D. Okay, so let's now process the vertex D. We're going to look at each of its unprocessed neighbors. One of its unprocessed neighbors is B, so let's find the cost of B. That's going to be the minimum of the cost we previously had, which is 8. That was not updated, so it's the minimum of 8. And whatever cost we had up to D, so the weight of the path up to D, plus the weight of the edge from B to D, which is 2. So the weight of that edge is 2. And so we see that the minimum of those two values is 6. So B will be updated. The cost of B is updated to be 6. What are other neighbors of D? Well, the cost of F. F is another neighbor of D. So the cost of F is the minimum of the previous weight of F, or the previous cost of F, which was infinity, and the cost up to D, which is 4, plus the cost or the weight from D to F, which is 6. So it's the minimum of infinity and 10. That's 10. G is another neighbor of D. So the cost of G is the minimum of its previous weight, which was infinity, previous cost, which was infinity, and the weight of the path up to D, which is 4, plus the weight of the edge from D to G, which is 3. So it's the minimum of infinity and 7, which is, of course, 7. And H is not a neighbor of D, so that's still going to be infinity. E is also a neighbor of D, so the cost of E is now going to be the minimum of whatever the cost was before, so that previously was 7, and its new cost, the cost of the path up to D plus the weight of the edge from D to E, that's 1. So a minimum of 7 and 5 is 5. So this is going to be updated. And now we have looked at updated the costs of all of the unvisited neighbors of D. So D has now been processed, and we're looking at the minimum of all unprocessed costs for vertices. E has the minimum of all of those costs, so we can update the path for E, and we can now go ahead and start to process E. So processing E, looking at all of its neighbors. So E has only one unvisited neighbor, and that's G. So let's look at the cost of G, and that's going to be the minimum of the previous cost of G, which was 7, and the cost up to E so far, which was 5, plus the weight of the edge from E to G, which is 1. So we've got the minimum of 7 and 6, which is 6 for G. E has no other unvisited neighbors, so the other costs will not be updated. They'll just stay the same. And now we have processed the vertex E. So we've processed E, and we are going to bring down the minimum of all of the costs. There are two unprocessed vertices of minimum cost, B and G. It doesn't matter which one we choose to bring down. Let's bring down B just because it's first alphabetically, but you could do the other one and the algorithm would still work. And so now we are going to process the vertex B. Because we're processing it, that means that the shortest path has been found. We look at the last place where the cost was updated, that was at 6. And because it was updated here most recently, that means that the edge from B to D is the edge that continues the shortest path. So we now know the shortest path from S to B goes from S to C, C to D, and B to D. But we don't have to look all the way back. All we have to add at this point is just the new edge from the parent D to B. Okay, we'll now process B. Let's look at each of its unvisited neighbors. The only unvisited neighbor that B has is F, so the cost of F is the minimum of F's previous cost, which was 10, and the cost up to B so far, which was 6, plus the weight of the edge from B to F, which is 13. So we're talking about the minimum of 10 and 19, which is 10. So the cost of F is not going to change. And we see that B has no other unprocessed neighbors. So out of all the unprocessed vertices, this one is still cost of 6. This one is still cost of infinity. The processed ones we don't have to consider. We could keep bringing these values down, the 0, the 2, and so on, but we can also just leave them as done. Okay, so now we've looked at all of B's neighbors, so B is processed. We're now going to process the next vertex of minimum cost, so that's G. So we're processing the vertex G, and because we're processing it, that means that we can look to where the last place was that G's value changed. That was at E, so E is the parent to G in this minimum path. Okay, so let's process G. Let's look at all of its unprocessed neighbors. So that's F and H are its unprocessed neighbors. Now the new cost of F in this round is the previous cost, so the minimum of the previous cost, which was 10, and the cost up to G, which was 6. The cost up to G was 6, plus the cost of the edge from G to F, which is 2. So it's the minimum of 10 and 8, and now that has been improved, so the cost of F is improved to 8. And the other unprocessed neighbor of G is H, so the cost of H is going to be the minimum of infinity and the cost to G so far, plus the cost of the edge from G to H, which is also 6. So it's the minimum of infinity, and 12, which is 12. So now G has been processed. We're looking at the minimum cost of all of those vertices. 8 is the minimum cost, and so F will be processed next. F's parent is the last place where a change was made, so F's parent is G, and this is the highlighted edge of the minimum path. Now we can process F. So we're looking at all the unprocessed neighbors of F. There's just one, and that's H. So the cost of H is now going to be the minimum of its most recent cost, which was 12, and the cost to get to F. So 8 plus the edge weight from F to H, which is 3. So the minimum of 12 and 11 is 11. So this is now updated as 11. And we've now processed the vertex F. Among all unprocessed vertices, well, there's only one left, and so the minimum weight is 11, and now H can be processed. H is being processed, so we've got its most recent change happened from F. So F is the parent in this minimum path, and we don't have any unprocessed neighbors of H to look at. So now H is sort of vacuously processed, and now there are no unprocessed vertices, so we are done with the algorithm. We see that we now have a rooted spanning tree. So rooted spanning tree with root S, and the highlighted edges show the edges of this rooted spanning tree, and these edges show the shortest paths, or the minimum weight paths, for each vertex of the graph from the starting vertex to each vertex of the graph. So for example, from S to F, we have this sequence of edges, this shortest path from S to F in this rooted spanning tree.